Today we're going to be talking about how to find the scalar and vector projections of the vector b onto the vector a. So the scalar projection of b onto a and the vector projection of b onto a. In this particular problem, we've been given two vectors. One is the vector a, which is 2i minus j plus 4k. The other is the vector b, which is equal to j plus 1/2 k. As a reminder, I've written the formulas for the scalar projection of b onto a and the vector projection of b onto a. The most important thing to notice about the formulas is that we're going to be using the scalar projection as part of our vector projection formula. Notice that the scalar projection is the dot product of a times b divided by the magnitude of a, which is also the length of the vector a. That goes directly into our formula for the vector projection of b onto a. You can see it right here. And all we do is take the scalar projection of b onto a and multiply it by the unit vector in the direction of a. That'll give us the vector projection. So the vector projection we write as the projection of b onto a, PROJ projection of b onto a. You'll notice that the scalar projection is written here COMP of b onto a. The reason we have comp instead of something like SCAL for scalar is because the scalar projection is also called the component of b along a. So we write it like this, component of b along a, and for the vector projection, projection of b onto a. So really we just have our formulas here and we need to apply them. We want to go ahead and extract the components of a and b from these vector equations here. So a is just going to be equal to, we should know how to do this by now, we just take the coefficients of I, j, and k and put them into a different form here. So the coefficient of I is just 2. The coefficient of j, when we include this negative sign here, is -1. And the coefficient of k is +4. So these are our direction numbers or our components of the vector a, and we can just say that the vector a is 2, -1, 4. Same thing here for b, keeping in mind that we have no I component. So what that tells us is that the coefficient on the I term is 0. So our vector b is going to be 0, +1, because 1 is the coefficient on this j term here, and then +1/2, which is the coefficient on k. It's easiest to write out these direction numbers, and then that makes it really easy for us to find the dot product of a and b, which we're going to need for both the component of b along a and the projection of b onto a. So let's go ahead and find our dot product of a and b. So we'll say a and b, dot product of a and b, is going to be equal to, remember that when we take the dot product, we just multiply the components of our vectors a and b, and then add the products together. So the x component of a is 2, the x component of b is 0, so we're going to multiply those x components together, and then add to that the product of our y components, -1 and +1, and add to that the product of our z components, 4 and 1/2. Like this. That'll be our dot product. If we simplify, we get 0 minus 1 plus 4 divided by 2, or 4 times 1/2 is just 2. That's going to give us -1 plus 2 is a +1. So our dot product is equal to +1. That's going to be the dot product of a and b. Now you can see to find the component of b along a, or the scalar projection of b onto a, all we need to find is the denominator here, which is the magnitude of a. That's also known as the length of the vector a. Remember, our vector a here is 2, -1, 4. Really all we're doing is using the distance formula to find the length of the vector a. This vector is really just saying that the initial point of the vector is at the origin 0, 0, 0, and goes out to the point 2, -1, 4 in three-dimensional coordinate space. So if we use the distance formula to get the distance between 2 points in three-dimensional space, we can say the distance of the vector a, d sub a, is equal to the square root. And here's where we would say quantity 2 minus 0 squared plus quantity -1 minus 0 squared plus quantity 4 minus 0 squared. But because we always have this -0 because we start at the origin, it really isn't necessary to write that all out because it's just going to simplify to 2 squared plus -1 squared plus 4 squared. So all we really have to do is take these direction numbers in A and square them under a square root sign. So we just have 2 squared plus negative 1 squared plus 4 squared. We just take our direction numbers, put them under the square root sign like this, square each one, and then we're going to get square root of 4 plus 1 plus 16, which of course will give us the square root of 21 as the length of our vector A. And this is of course equal to the magnitude of A, which is written like that. Now we have the dot product of A and B, and we have the magnitude of A. That's everything we need to find the scalar projection of B onto A. So we can say that this is equal to the dot product of A and B, which is 1, divided by the magnitude of A, which we know to be root 21. This is our scalar projection of B onto A, also written as the component of B along A, like that. Now all we need is the vector projection of B onto A, and since we already have the scalar projection, that's going to be really easy to find. So the projection of B onto A is going to be equal to, we just take this value we found earlier, 1 over root 21, and we plug it in for this piece of our formula here because it's the same. So we have 1 over root 21. We multiply that by A over the magnitude of A. Well, A we already have is 2i minus j plus 4k. So we're going to multiply this by 2i minus j plus 4k. We take the vector in its original form. Then we divide that by the magnitude of A, which we already know is square root of 21. We found it down here when we used our distance formula. So we're going to say divided by square root of 21. Now if we just simplify this, what we're going to get is in our numerator 2i minus j plus 4k, and in our denominator, root 21 times root 21 is just going to give us a positive 21. Now we could leave it like this, but technically, if we want to be precise about our answer, we want to distribute this 1 over 21 across each of our components here. So we're going to get 2 over 21i minus 1 over 21j plus 4 over 21k, and that's going to be, of course, the projection of B onto A, the vector projection of B onto A. And this is the best way to write our final answer for the vector projection of B onto A. So that's how you find the scalar and vector projections of B onto A given the equations of two vectors.